All right, 4025 MAA mechanics. This is tutorial number 4. We are talking about internal forces. Now, this question says determine the internal normal force, shear force, and bending moment at point D. Now, this is a particular structure here. There is D. This is the point D for which you want to find what's going on inside this point. Question for you. We have to do the free body diagram. Of course, we need to know, well, in order to find, let me write it here. In order to find internal forces, we need to have complete information about the external actions and reactions. But let's say external loads. So this is including reaction forces. So the very first thing we have to do here is to find the external forces, which is this one, and all the reactions from these supports as well. Now, what do we have here? We need to do, since we want to know what's happening here at point D. That means I can just do the free body diagram. So free body diagram of the beam. This beam A, B. Yeah, beam A, B. So that also means I have to look at this constraint and this constraint. Now, what kind of constraints are these? Now, this one is a pin joint. This one is a pin. And this one is a rod. This is a truss. It's pinned here. It's pinned here. So it's pinned at both sides. That means it's a truss member. Truss member. And you know that truss members can only react with a force that is in the direction of the truss. All right? Very good. And so we also have here, we have two forces. But now I'm going to show you that this is not the best way of saying, of stating these two forces because, well, because we want to choose a reference system that is smarter than vertical and horizontal. Since we know that these things, this force is acting in this direction, and this force is acting in this direction, that means the best use of a reference system is to have it inclined like this. So that this force is along the y-axis, this force is along the y-axis, and this pin, I told you, this pin reacts with a set of two perpendicular forces. Again, it doesn't matter as long as they are perpendicular to each other. It's the same thing because you can always split them and recombine them in different directions. So the idea is that the pin reacts with two forces that are perpendicular to each other. And that's it. So it doesn't matter where, how they are angled, as long as they are perpendicular to each other. So since I have called this one X and this one Y, I'm going to call this reaction AY and this reaction AX. And this one I'll call it BY because it's applied at point B. All right, so let's do this. So this is the free body diagram of the beam. So at point A, then we have point D. Point D. Then we have point B. And then we have this point here, which to the force is applied here. So this is a force here of 60 newtons. Then we have the reaction force By. Then we have the reaction force Ay. And we have a reaction force Ax. Okay, that's it. So these are the only reactions. So how do we solve this one? Very easy. Just apply equilibrium equations. Let's apply the equilibrium equations to this beam. Equilibrium equation X, Y, Z. For Z, I'm going to choose point A as the reduction pole of the moments. So along the x-axis, we have that Ax equal to 0, very easy. Ay plus By minus 60, Ay plus By minus 60 equal to 0. That's my second equation. Remember, this is the reference system. This is the y-axis. And this is the x-axis. And the moments, well, we're doing moments about this point here. That means the only moments we have to care about is this one. So this, you know, this distance is 1 meter. This distance is 70.75 meters. Okay, so this, my drawing is off, but doesn't matter. But we don't know, apparently we don't know how much is this. So what's this distance here? Can we find out? I think we can. How do we find out? Well, let's look at this triangle here. We have a triangle. Looks to me that this is 90 degrees. So this is 60 degrees and this is 30 degrees. And we also have the hypotenuse of this triangle. So we have the hypotenuse and we want to know this distance AB. So this distance here is just, so this distance here is just 2 meters times the cosine of 30. Okay. And so that means we have, this is equal to 1.73 meters. Okay, that's the idea. And so what we do is A, so this gives no moment around A, this gives no moment around A, this has a moment of By, it's a positive moment counterclockwise, so it's By times 2 cosine 30, so it's 2 cosine 30 times By, this is the moment of By. And this force here is, of course, clockwise around A, which is minus 60 times, how much is this? Well, this is just this distance plus 70.5, so sorry, 0.75. So this is negative, this times, let me put it down here, 2 cosine 30 plus 0.75 equal to 0. This is the other equation. So we can find By from this equation here. By is, let me do this in red. So as a result, we get that By is 60 times 2 cosine 30 plus 0.75 divided by 2 cosine 30. That's equal to, can you do this calculation for me, please? I'll try to do this using the calculator I have here. So it's 60, let me put this here. Two times cosine 30, as we said, is 1.73. So if I do the inverse of this times 1.73, sorry, 73 plus 0.75 times 60 divided by 1.73, it should be about 86 newtons. 86 newtons. That's By, and so we can get Ay from here, and Ay is 60 minus 86. Ay is 60 minus By, which is just minus 16, no, minus 26 newtons. So that means that Ay goes in the opposite direction, but we don't care. And that's it, Ax is 0. Ax is 0, this is already a solution. All right, what do we do now? We want to find what's happening here inside D. This is D, so I must cut here. And where do I look? I can look left or I can look right. Now, which one is the easiest one? What do you think? Come on, in chat, which one is the easiest one? And does it matter? It doesn't matter. So I can cut at D and look left or right. Now, I'm looking left because I think it's easier. I choose left. I choose left. So if I choose left, I have to draw everything that is on the left of point D. That means I am looking at this. This is point D. This is point A. Then I have that this is this AY. So AX is 0, so I'm not drawing it. And AY is minus 26. So let me draw it down here. Let's say this is 26 newtons. And now I have to draw where I cut here, I must expose the internal forces. Internal forces, remember, the internal forces are always, remember the Santino I told you about. This is plus. Then you have the normal force, goes like this, positive in tension. Shear force goes like this. And bending moment is positive when smiling. So since we are looking left, we are using this side because we are exposing the forces on the right. So this means this is N D. This is VD, and this is MD. Now that means that under the influence of these three loads, three internal loads, we are maintaining equilibrium here. Now, how much is this distance? This distance is not given. What we can find out is this distance, 1.73 minus 1. Okay? This distance here is 0.73. Agreed? That's what's going on. So I can just use equilibrium equations again, equilibrium equations along X, along Y, around Z. Z, I'm choosing the cutting point because it's always the smartest choice in this case. So I can say that ND equals 0. VD is minus 26 because that's the only force that it must balance. VD is minus 26 newtons. So the equation is minus 26 minus VD equals 0. Let me do this here. The equation is minus 26 minus Vd equals 0. But this equation is just Vd. It's minus 26 newtons. And the moment is we have Md, which is a positive moment. This one gives no moment. This one gives no moment about D because they are passing through D. This one has a moment, as a positive moment of 26 times 0.73. So this plus 26 times 0.73 is 0. So that means that MD is 26 times 0.73, 18.98. Let's say, I'll say 19, minus 19 Newton meters. There you go, found. So these are the results of normal force. So there is no tension or compression. In this point here, we have no tension or compression. We have some shear and we have some moment. Now, what is the bending moment? Bending moment means this beam is frowning. Okay, so in fact, if I look at this action here, this tends to curve the beam in this direction. Okay, so the beam is frowning. All right, any questions on this? No questions? Going good? All fine? Right. Let's do exercise level 2. Now, again, this is another structure. We want to determine what's happening inside point C. So at level of internal forces. I'm going to need this. Remember, this is the Santino we need. Put it here. Duplicate. There we go. It's here. It's always available. So, I don't know. Let's do this. How many reaction forces we have here? So this is, we need to do free body diagram. Remember, step 1, always find reactions. Step 2 is cut and look left or right. And step 3 is solve for equilibrium. So find reactions. What is this in B? How many reactions we have here in B? Here in A, it's easy. This is a pin joint, so we have AY and AX. Yeah, Kata says 1. Which direction? Can I ask? Which direction is this reaction force going? Is this horizontal, vertical, this like this? Come on, we have one reaction force. Nabu says horizontal. So this is an horizontal roller. This can slide left and right. So if this can slide, it doesn't react left and right. But what it doesn't allow is this movement. This movement is not allowed. So that means that there must be a reaction force, Vy, that's keeping it from moving. Okay, so that means if I do this, I get AY, I get BY, I get AX, make this shorter. I have AX. And what do I have here? I have something, let's say something like this. With an active force of 400 newtons. Do we care about what's happening inside here? We don't care. We want to know what's happening here. So for all intent and purposes, this thing is just applying an external force at this distance here, 1 meter away. It's 1.2 meters away. So you should agree with me that this distance here is 1.2 meters, okay? Because it's 1 meter from here to here. It's 1 meter from here to here. And then you have 0.2 meters, the radius of the pulley. Okay, so it's 1.2 meters away. All right, so let's do the equilibrium equations of this to find the reaction forces. So equilibrium equations. We have along X, along Y, and around Z. Again, I didn't explicitate what is X, what is Y, but okay, this means we are just using the usual ones. And so we have along X, we have AX plus 400 equals 0. You agree with me? Possibly yes, and that means that AX is minus 400. This is the result, not the reaction force. Then we have that AY plus BY equals 0. That's all we can say. And regarding Z, let's choose A again as my pole of reduction. So this gives no moment, this gives no moment, but this gives moment, this gives moment, and this also gives moment because they are not passing through A. Now, the moment of this one, this force is rotating around A in a clockwise direction. So it's minus 400 times the perpendicular distance between A, point A, and this is point B. This is point C that we want. So the perpendicular distance between A and 400 is this one, 1.2 meters. 1.2. And BY is giving a positive moment counterclockwise, so plus BY times the distance, this distance here. How much is this distance? 3 plus 2. So this is 5 meters. So this distance is 5 meters. BY times 5 equals 0. So that means that I can solve BY first. I will solve for BY in this equation. I can say that BY is 400 times 1.2 divided by 5. 400 times 1.2 divided by 5, 96 newtons. And this one, that means that AY is minus 96 because they must be equal and opposite to keep equilibrium. Minus 96 newtons. So we have, these are the results. These are the 3 reaction forces. Very nice. Now, step 2. Step 2. Cut at C, in this case, and look left or right. Where do I look? Where do I look? Do I look? Do I look left or do I look right? Which one is easier? Let's cut at C. If I cut here at C, which one's easier? I believe we all agree that the left-hand side is easier. We only have 2 forces. Here we have all these things that we have to draw instead. So let's look left. So I choose left. Let me take this down here to the next page. So we are looking left. That means I have to draw whatever is on the left of C. So this is the beam, the chunk of beam that is left of C. And then we have in AY is minus 96, so that means it's going down 96. AX is minus 400. So we have this 400. And this distance between A and C, this distance here is 1.5 meters. All right, there you go. There's nothing else needed. We need to copy the Santino here. There you go. Take this one, put it here. Now, of course, this is VC, this is MC, and this is NC. All right. So equilibrium equations again. Meaning we have X, Y, and Z. And the first equation is minus 400 plus NC equals 0. And the second equation is minus 96 minus VC equals 0. And the last equation is MC. So let me put this in green. The second equation is MC. So this gives no moment, because it's also passing through C. So the only moment is this one, which is positive. 96 plus 96 times 1.5 equals 0. So if I solve these, well, let me put this here because I want to say that this is step 3. So this is step 2. Yeah, and this is step 3. Solve equilibrium. Well, expose internal forces and solve equilibrium. All right. This is what I was saying. This is XYZ, and so this turns into a system that has NC is negative 400, and that means compression negative 400 newtons. VC is minus 96 newtons. We don't have a name for that. And MC is 96 times 1.5, 144. Negative. MC is negative 144 Newton meters, of course. And this is frowning. Right? Let's have a look. If this pulls, that means that this beam will tend to deform like this. Okay. Do you agree with me? Possibly, yes. You must, because this is correct. These are the 3 results that we're looking for. Okay, now let's do the last one, which is also, it's more of the same, but this is a bit more complicated because we have an internal constraint here. Let's see what's going on. Let me copy the convention first. Here. So what's going on here? Determine the internal normal force, shear force, and moment at points D and E in the compound B. Point E is located just to the left of this 10 kilonewton load. Remember what I told you in the lecture. You can't find it, what's happening exactly here, because it would be like me asking, what's going on here? Let's say, what's happening at 2? This is 1, this is 2. So what is the value of this function at 2? You can't tell me because it's got 2 values. So you can tell me, okay, it's 1 if we are approaching it from the left, and it's 2 if we are approaching it from the right. So that's what is saying, that point E is located left. So that's say approaching from the left. That's the idea. Assume the support A is fixed. So this is a fixed support. And the connection at B, which is this one here, is a pin. So we have an internal pin. It's not an external pin, it's an internal pin. Now, the external pin, if you have an external pin, this reacts with 2 forces and no moment. And that's exactly the same that's going on here. For internal pins, imagine an internal pin is something like this, for which you can rotate. You can rotate about the 2 ends. So the internal pin, as I said, it's the same thing. So it doesn't transmit bending moment. You know that the bending moment at B is 0 for sure, 100%. Okay, so let's do the free body diagram. If I do the free body diagram of this looks like this. So it's exactly in the middle. This is the internal pin at B. At A, we have a fixed support. So we have how many reaction forces at A? We have AY for sure. We have AX for sure. But we also have a moment, MA. These are the 3 reaction forces that you have for a fixed support. We have a distributed load here. Okay, very important. Remember, we have to know how to treat distributed loads as well. And this is 2 kilonewtons every meter. And we have another active force of 10 kilonewtons here. Point E is right here, just to the left of it. And point C is a roller, looks like a roller to me. So that means that at point C you have CY. We have a problem here. What's the problem? Can you see what's the problem? We have 4 unknowns. 4 unknowns and only 3 equations. 4 unknowns. Only 3 equilibrium equations. So how do we solve this? You can't solve a system of 3 equations and 4 unknowns. So what's the information that we have? The information that we have is that if we cut in B here, we know that this one and this one will be 0. And so you have 1 fewer unknown if you cut. So if we look right, say, we can look left or we can look right. But let's look right. Cut at B and look right. Cut on B and look right, you get this condition. CY, which is still unknown, unfortunately. Then you have 10 kilonewtons here, in the middle. And then you have, if I'm looking right, of course, I must use this side of the convention. So I have here, this is B. So I have the normal force in B, which is non-zero. The shear force in B, which is also non-zero. And we have no moment. So I'm not even drawing it. We have no moment. In B, there is no, here, no bending moment. Important, okay, very important. It's no bending moment, no bending moment. And so I don't draw this. This is zero. And now let's have a look. If you look at this, you only have three. You have three unknowns: NB, VB, and CY. But we also have three equilibrium equations. Now we have three unknowns. And so let's solve equilibrium. X, Y, Z. Now that we have equilibrium, we have NB minus NB equals 0. That means NB equals 0. VB minus 10 plus CY equals 0. So we can't solve this yet. But we know that, what's this? This is 3. So this distance is 1.5 and this distance is 1.5. So we have that CY, so 3 times CY minus 10 times 1.5 equals 0. So we can say that CY is 15 divided by 3 is 5 kilonewtons, because we are using kilonewtons here. And that means that VB is 10 minus 5 is 5 kilonewtons, of course. There we go. And then B is 0. Okay, now we found the reaction force. Now that we found this one, we now can go back and find AX, MA, and AY. Okay, so let's now go back to this one more time. We can now go back to the original, to the entire free body diagram to find the other 3 unknowns reactions. The other 3 unknown reactions. So this one, CY, we said is 5. So this one, I'm going to say this is 5. Now we have 3 unknowns. And now we solve it. So remember this, how do we treat this one? How do you treat this? This one is equivalent to a single force applied in the middle. And this force, this equivalent force, is, how much is it? It's 2 kilonewtons per meter over these many meters. This is 3 meters. Okay. So it's 2 kilonewton per meter times 3 meters equals 6 kilonewtons. This equivalent force is 6 kilonewtons applied at 1.5 meters away. So let's do equilibrium. X, Y, Z. I'm going to choose point A. And so we have along X, there is nothing. I don't see, there's just AX equals 0. There you go, easy. Along Y, we have AY minus 6 kilonewtons minus 10 kilonewtons plus 5 kilonewtons equals 0. So we can find AY quite easily. So AY is 16 minus 5 is 11 kilonewtons. AX equals 0, this is already a result. And finally, we have that MA, this way, this is positive, counterclockwise, so we have MA. This is negative, minus 6 times 1.5. This is negative, minus 10 times 4.5. 3 is 1.5, 1.5, 1.5. So this is 4.5. And this is positive 5 times 6 equals 0. So that means that MA is 6 times 1.5, 9, plus 10 times 4.5, that's 54, minus 30, 24. MA is 24 kilonewton meters. Okay. Did we solve the question? Not yet, because we want to know what's happening in D, what's happening in D, and what's happening in E. So now that we have the external forces, now we have all external forces. We cut in what was the point? D and E. D and E. Well, we cut in D and look left or right. And then we do the same for E. So let's start with D. If I cut here, what happens? This is D. Where do I look, left or right? I believe since left is shorter, I'll probably look left. Let's look left. So this is D. We know there is a distributed load here. Distributed load is been cut in half as well. Okay, so you are cutting also the distributed load. This is 2 kilonewtons per meter always, but now this is only 1.5 meters. Agreed? We said that AY is 11 kilonewtons, so this one is 11. AX is 0, so I'm not drawing it. And here we have to use the the right-hand side of the Santini. This is MD, this is ND, and this is VD. And then there you go. Now again, this is also this. I told you this is a distributed load. So this means you have to do one more time, find the equivalent force. F equivalent is now 2 times 1.5, which is 3 kilonewtons, applied at, in the middle, 1.5 divided by 2, all right? That's why it's very important that you don't, once you find the equivalent force, it's the equivalent force for that load. But if you're cutting the load in half, see, if you cut the load in half here, it's not 6 kilonewtons anymore. Now it's 3, of course, because it's been cut in half. And it's not applied at 1.5, it's applied at 1.5 divided by 2. Very important. This is one of the greatest sources of mistakes at the exam, which is just an extraction error. Okay, that's the idea. This is around D. So ND equals 0. Very easy. VD, so minus 11 minus 3 is this. Okay, we have condensed the distributed load into the equivalent force. So 11 minus 3 minus VD equals 0. That means that VD is 11 minus 3, which is 8 kilonewtons. And finally, MD. We have this one, which is negative, and this one, which is positive. So MD plus 3 times 1.5 divided by 2 minus 11 times 1.5 equal to 0. So this gives MD equals 11 times 1.5 is 16.5 minus 3 times 1.5 divided by 2 gives 14.25 kilonewton meters. There you go. This, and this is what's happening at point D. And remember, this is positive, so this is smiling. And well, last thing is now we cut in D. Finally, we cut in E and look left. Well, in this case, let's look right, which is easier. If I take here cut in E, and look right. See, since E is on the left of the 10 kilonewton load, if I look right, I have to include the 10 kilonewton loads as well. So cut in E, look right means go here, draw this, make it thicker. This is the cut. So this is point E. We have here the 10 kilonewton load applied exactly at E, although it doesn't look like, but it is applied at E. And then we have, what do we have on the right? Also the 5 kilonewton of CY. This is 5. And finally, we need to draw the internal forces, which since I'm looking right, I must use these ones. There you go. And let me take care of this. Say that E is this. This is an E. This is VE. And this is ME. What's this distance? Again, I believe this distance is the same. Yes, this distance is 1.5. So we have everything sorted out. 1.5 meters. So equilibrium equations. X, Y, Z around E. And we have that NE equals 0. Very easy. There are no horizontal actions. VE plus no, minus 10. Minus 10 plus 5 equals 0. And that means that VE is minus 5 kilonewtons. And finally, we have minus ME, because it's a clockwise moment. ME is a clockwise moment. Look at this. This goes like this. Minus ME. This 10 kilonewton does not have any moment about E because it's passing through E. So the only thing that has moment is 5. So this is a positive moment. 5 times 1.5 plus 5 times 1.5 equals 0. And that means that ME is how much? How much is 5 times 1.5? Help me out. 5 times 1.5, 7.5 kilonewton meters. Again, this is positive, so smiling. This, and this. Any questions? How does it look like? Looks good. So this one, level 3 exercise was a bit more complicated. You had to think about it a bit, but nothing impossible. You also have to remember some previous knowledge about the equivalent loads and how to treat distributed loads as well. Okay. Any questions? No questions? All good? I'm waiting for you in the chat. No, sir. All good. Very good. I mean, this is a bit more complicated than you will get at the exam, but at the exam, it's very likely you'll see something like this. Okay, so make sure that you at least know how to use, deal with distributed loads, rectangular loads. All right, yeah, we solved all the questions. Everything seems fine. So I'm going to stop recording right now, and I'll see you next week. Thank you. Bye. Stop recording.